Hi, good afternoon, everyone. The first presentation today will be from Elie Libbos. The topic for his presentation is variable pole induction machine for electric vehicles, and he's working with Professor Arjit Banerjee on this topic.
All right. Hi. Today I'm going to present variable pole induction machines in electric vehicle applications. So my outline, first I'll give a motivation to why we actually need to change pole in electric vehicles, and then I'll introduce pole changing induction machines, and I will say how to optimize with these induction machines, taking into consideration the current constraint and the real practical constraint, and I'll talk later about my current research work. So I'll first talk about my motivation. As you see, the permanent magnet synchronous motor is dominating the electric vehicle industry. Mostly 80% of the motors are based on permanent magnet synchronous motors. There's still 17% based on induction motor, and the rest are negligible. So what's that advantage that PMSM has over induction machine? This advantage is in itself in its magnetizing current. The induction machine has a magnetizing current which doesn't exist in a permanent magnet. In a permanent magnet, you have your magnet and that's it. In an induction machine, you need to create your magnet electrically, and you pay that price in terms of efficiency and power density. So here are some, for example, designs. Tesla were priorly using induction machines, and then they switched to permanent magnet machines. And you can see that Audi in 2018, I think, launched the first electric SUV, which has 2 induction machines. So although they're not commonly used as PMSM, they're still used. But all of the induction machines used so far in electric vehicles are fixed pole induction machines. And one main point is that you pay the price of magnetizing current, right? But what you gain is flexibility. In an induction machine, you can shape your magnet the way you want electrically, while you can't do that in permanent magnet machines. So that's the main advantage, which I'll talk about. So why do we need to change poles in an electric vehicle application? This is the same induction machine configured as 2-pole, 4-pole, and 6-pole. As you can see that at low speed, 6-pole has a very, very high torque capability, which is desired in an electric vehicle. But it loses its torque capability rapidly. While at high speed, the 2-pole configuration can supply the torque at the maximum speed, which we usually refer to as cruising torque, while a 6-pole machine is very weak at this point. And this applies for all machines, not just for induction machines. So in order, if you use the 2-pole configuration at high speed and the 6-pole configuration at low speed, you don't need to sacrifice in your design meeting both the high-speed consideration and the low-speed consideration. But this is only from design perspective. What about from operation perspective? Because most of the time, the electric vehicle is not operating at its rated conditions. In any realistic drive cycle, couldn't add any image here, but you will operate mostly all within that range. So it's not actually at the rated point. So what about these points? Let's take 2 examples, point B and point A. They're operating at the exact same speed. For point A, selecting the number of poles is relatively easy. You only have 6 poles that can produce this torque. But at point B, 2-pole, 4-pole, and 6 poles all can produce the torque. So how do you select your number of poles? That's an additional degree of freedom you gain, but you need to select first your strategy and optimize. You can optimize efficiency, you can do anything. You have an additional degree of freedom that you can exploit in these operations. So now I'll introduce pole-changing induction machines. So here is a toroidal machine that Matt McGill built during his PhD thesis. So what I love about this machine is it has access to each of its slots. So if you see, the induction machine, the toroidal machine is wound like a transformer. So you have slot 1 and its return conductor, slot 1 prime, right behind it. And then you have external access to all of these slots, which means you can create any magnet shape you would like. Of course, in real life, you have power electronics constraint, thermal and magnetic constraint of the machine. Now, one of the classical techniques applied to change pole is called pole phase modulations. So I'll try to explain physically what that formula means. Think about if you have 36 slots in a machine. If you want to operate 18 phases, how many times can you repeat the pattern? Twice. So it's a two-pole machine. If you have 9 phases, you can repeat the pattern 4 times, which makes it a 4-pole machine. At 6 phases, at 6 poles, you have 6 phases. I'll skip these for the time being, but I'll come back to them. You have 12 poles and 3 phases. So the beauty about pole phase modulation is that it maintains power balance. You don't have single phase operation. So single phase will cause double frequency, fundamental frequency ripples, which will be very hard to take care of from a power electronics perspective. So this mostly simplifies. It forms a balanced system from the DC side perspective for any pole number. But when I did my calculations for 8 poles and 10 poles, I noticed that they need 4.5 phase system and 10 3.6 phase system. And I saw in all the literature, everyone just threw them away, like they don't exist. So I asked myself, can we in a sort of twisted way just have a 4.5 phase system? And it actually works. A 4.5 phase system is an average of a 6 and 3 phase system. It forms a 4.5 phase system that forms a 4-pole magnetic field in the air gap. But I didn't kind of like the explanation because it was so math involved, I couldn't even explain it. So I tried to come up with an alternative explanation to PPM that gives insight on how an 8-pole, for example, 4.5 phase system works. So here, I looked at, if you go back to this figure, if you have 2 slots and you have 36 slots, 2 adjacent slots will be separated by 10 degrees mechanically. So if you look at slot 1 and slot 2, if you look at their currents, if you're operating at the 2-pole machine, the electrical phase shift must be the same as the mechanical phase shift. So you just put a 10 degrees phase shift. But if you want to operate at a 4-pole, you double the electrical phase shift for the same mechanical slots, which are separated by 10 degrees. If you want to operate as 8-pole, which was a non-intuitive phase system, you just use a 40 degrees phase shift, and that's it. That's a way simpler explanation, and it works. So why am I stressing about these poles? Because sometimes if you do pole jumps, as I will show later, you don't actually get the benefit of changing poles. There are practical limitations that will limit you. So you don't want to jump from 6 to 12 directly. That's not a good jump to do from a pole perspective. So here I show the FEA simulations, which show you all of these operations. And this is 2-pole, this is the 8-pole 4.5 phase, and 10-pole 3.6 phase system. And now I will talk about the power electronics. So what I wanted to do is to look at what is the main fundamental building block to form a balanced system. And I realized that typically in the literature, if you have 18 phase as the highest phase system, you just put 18 inverters in parallel, and that's it. But I wanted to look if there's more fundamental building blocks that would make it easier, and I realized you can do this with 9. And the beauty about it is that you have 9 independent inverters. So you can configure them any way you want. You can connect them from the DC bus perspective in series. You can clap them in parallel. You can do a lot of things in this aspect. You can do maybe some twisted way of not using all 4 converters and coming to the conclusion, to the same results. I don't know yet, but maybe it can be done. So one of the main things about this, although in this design I'm still using high voltage switches, your voltage, DC bus voltage now is required only for 1 slot. So it's a relatively low voltage architecture now. And low voltage devices have lower on-state resistance, although I have a lot of switches, but they have lower on-state resistance. And one thing is that the power you're switching now is the power only for 1 slot compared to other motors. So your switching loss will definitely decrease. So you will gain an additional temperature range also to operate near the motor because the loss per switch is smaller now. So now, I introduced pole changing machines, but how do we actually use them in an EV? How do we benefit from them? Because pole is an additional degree of freedom we get that is not available in any other machine. And as I said before, from a drive cycle perspective, you're not always operating at the rated condition. You want to know where do I use which pole. So this is one of the formulas we derived. And when I looked at literature, I saw sometimes that they get, if you jump from, let's say, from 2 to 4 poles, you will double your torque. From 2 to 6 poles, you will get 3 times more torque because your pole is a factor outside. but they never actually considered thermal limits. So what they actually do, I saw some design where they jump in poles, expect a 6-time jump in torque, and then at the end they get the same torque. So I didn't want to reach the same end. So I tried to look at, all right, what's really going on here? And one of the main criteria is this current, the magnetizing current. It increases with square the pole factor. Imagine if you jump from 2 to 4 poles, you have 4 times more magnetizing current. Imagine you do a jump from 2 to 18 poles. You will have 81 times more magnetizing current, which can by itself exceed your rated stator current. So you have to weaken the machine, and then there's no benefit anymore of increasing that number of poles. So here I drew the torque capability. If we limit the current from 0 to 15 amps, for each current from 0 to 15 amp, the torque capability of 4 poles and 6 poles. And if you see that before a torque level of nearly 10, which is at point A, below it, you would actually like to use the 4 poles because it requires a lower current. But after point A, beyond point A, you would like to use a 6-pole configuration because it requires more current. So there's an optimization involved here where the pole numbers intersect, and where you would like to use in a certain region a 4-pole, in a certain region a 2-pole, in a certain region a 6-pole, and so on. And this is an idealist, and this formula is ideal, so it neglects leakage at the point and all resistances. And then you go to this, one of my favorite curves, because at the 18 poles, one of the papers I read, they didn't get any torque benefit. So we have to predict that beforehand. You cannot design and then say, oh, all right, I won't get any benefit. So what I plotted is I assumed my current rating is 15 amps. And all of these poles, I have their torque capability. What's the highest pole number that produces the highest torque? It's 8 pole. You see, 10 and 12 are still below it. So I don't need to actually use them. There will be no benefit of using them unless you allow an overload current of 25 amperes where you can use 10 poles temporarily. Of course, your power electronics has to allow that, has to be designed for that. So now, for illustration, I use the maximum torque per ampere strategy. So you can use maximum efficiency there, because it's maximum torque per ampere doesn't always yield the maximum efficiency. So there are a lot of strategies. So for illustration now, I picked one. And as you see, like in your high torque region, you would like to use an 8-pole. In your lower torque region, you would like to use a 6-pole, then 4, then 2. And there's at high speed, all of these becomes weakened after their synchronous speed. So now you would like 2 poles becomes more attractive. And then if you take a cross section at 0 poles, at 0 speed, if you take a vertical cut, you will see that the torque per ampere is starting to increase. And then once it starts to drop, we switch to 4 poles. Then we switch from 4 to 6. Then we switch from 6 to 8. We're always guaranteeing the maximum torque per ampere in all operating regions. And what's nice about this curve is that it starts to saturate at 8 poles, which is another indication that there's no point of going beyond that. And these are some of the experimental testing results. So in the experimental testing results, I had to, because I'm using only one converter for the time being, so I had to wire it as 2 slots per pole per phase. To make a long story short, the 4-pole is now the 4.5, what requires the 4.5 phase system. So if 4-pole operates, which means it's valid, the 4.5 phase system works. And it actually worked. And you can see it's a very easy strategy. These are the slots which are 40 degrees located mechanically. So I have control over the electrical excitation. If I make the electrical excitation 40 degrees as phase shift between them, I get 2-pole operation. If I make it 80 degrees, I get 4-pole operation. If I make it 120 degrees, I get a 6-pole operation. And you can see here the torque per ampere. So it started highest for 2 poles, then it reached for 4-pole highest, then it reached for 6-pole highest in the high region. So there's an optimization going on. So now I'm going to talk about my current research work. So I just mentioned the maximum torque per ampere strategies, but now that we have an additional degree of freedom, we can actually implement any strategy. And a more important strategy from an EV perspective is to maximize efficiency over the whole drive cycle, the whole operating region. Also, there's dynamic performance. Like I didn't consider it's all steady state analysis now. You cannot switch an EV and get a torque bump while you're driving. That's not something you want. And There's also the question is, can we simplify the power electronics further? Maybe use less switches or so. At least because 72 switches is still a long number, and we can do it with 2, 4, and 6, but the question is still from a dynamic perspective. The question remains. And thank you. Any questions?
Electric vehicle.
Yeah.
So as a car driver, what I really want to do is have a constant torque over the very wide speed range. So thinking when you're driving the car and you press the pedal, you want it to speed up at a constant rate. This is a constant torque. But I saw from your diagram you have a maximum torque at a very, very narrow speed range. So is there a way that you can expand the maximum torque into maybe half the speed?
Yeah, because you can use different excitation. Because at the end of the day, this happens at a certain frequency, right? The 8-pole where it starts to weaken, you're saying that. And because most EV require only the high speed at low torque, so that's a typical EV characteristic. I wish I put one in the slides, but it looks similar to the one here displayed. So you can shift all of these are fundamental frequency of 60 hertz. You can shift this, and you can also, there's gear involved. So.
I think because at the end of the day, we want to compare, if we want to high performance car, then you probably want to compare your work with a Ferrari, not a people.
Yeah.
Because that is directly head to head.
Yeah, but also this, like, if you save on efficiency, and you don't need, sometimes you can, or actually, I want to use only 3 combination of poles or 2 and save efficiency and have a simple drive. There's also this saving battery life, saving a lot of things going on, which will, basically Tesla said what made their, is the induction machine is cheaper than permanent magnet synchronous machine, but the overall cost is more expensive with having induction because of the battery sizing issue, because of the efficiency, because of these issues. So if you can make these issues and make it more power dense, then you will have probably, there must be a comparison at the end, I'm sure. And if you see this, for example, what's nice about here, the design, you can at low torques meet your low torques meet your specs from design perspective with high pole, but you don't have this high pole. It doesn't need to meet high speed requirements. And you just design that high speed requirement at low pole.
Could you go back to where you had the picture of the power converter? So you have 9 half bridges there.
Yeah.
And then there's 4 inverters on the diagram.
Yeah. Actually, this is only one of the 4 units. So this is this one unit.
So there's 36 of that?
There are 4 of that.
Each board has 9.
Each board has 9.5 bridges.
Oh, so you have 4 of these 4.
Yeah, 4 of these boards. Yeah. And here I'm still at this point using 650 volt switches, but at the end of the day, each slot required nearly 20 volts. So this power converter is capable of driving the whole machine without another converter. So that's still, I still oversized it at this point because I wanted that flexibility to have.
That makes sense. I forgot that you must have multiple ones. I was trying to boil it too.
All right. Any more questions? Oh,
yeah, so getting back to the question about wanting to have constant speed for the engine, for a regular car, this was gotten around by using your transmission with different gear ratios and all of that. Would your design be able to eliminate getting rid of the transmission? So you just have what's going on in the motor, you don't have to have this other internal thing that weighs more? Would your design be able to get rid of that?
That's one of the points I didn't go through yet, but I think it's definitely worth exploring, because if you...
Even if it requires, so the gearbox is required for reducing the size of the machine, because you don't want to run a 1800 RPM, you don't want to put an 1800 RPM machine, it's a big bulky.
Yeah.
So you want to go to a 20,000 RPM and then do a fixed stage gearbox reduction or gear ratio. You don't have to have a clutch, gear, and all those things for automatic transmission,
okay,
but it will be a fixed speed gearbox.
Okay.
And you can pick basically one of the poles where you will design it. You don't need to... If you design it at 2 poles, you might get different advantages. Or at 6 poles, I haven't looked at.
Look at it, if you go back to your first slide, when I was thinking when you were showing me this curve, this is like a gear change for
with a mechanical system.
Mm-hmm.
So you incorporate a gear change in the electrical system, and then you do a fixed speed gear ratio change.
Interesting. That sounds pretty cool.
But this has been explored before. So this is not the contribution of this work.
Okay, all
So
right.
people have looked at this for several times. Like one of Phil's student, Matt Megan, he worked on this. So this concept is not new.
Okay, all right.
But I'm sure it's new to you. So
It's new to me, yeah. So
sure,
that's
why.
interesting.
But it's
yeah.
very exciting to us as well.
Okay, all right, cool.
But do you think will that reduce the size of the gearbox if you make it a fixed speed instead of having a multiple gearbox ratio?
Well, I think you might be able to cut down on some of the weight requirements, and so then that might help with efficiency a little bit, because then your car doesn't weigh as much, so then you're not having to propel as heavy of a thing, so you can use, the torque might be going down.
My question is like, if you compare a fixed speed gearbox versus a variable, sorry, if it's a fixed gear ratio versus variable gear ratio, is there a benefit of having fixed gear ratio over variable gear ratio? From a mechanical perspective.
It would depend on the speeds that you're trying to operate in and the torques that you're trying to get out. So if you're able to vary that gear ratio, then you can change the amount of torque that's going to the tires that's coming out of the engine. Versus a fixed gear ratio, that torque transfer is fixed. So that might be one of the reasons why a variable gear ratio might be better than a fixed one for a given application.
No, from size perspective.
From a size perspective, well, it's definitely going to be smaller if you have the fixed gear ratio. It's only 2 gears versus the variable one. When a car, right now, it's got like 6 or 7 different gears that are in there. So size will definitely be smaller.
Perfect. Thank you.
You're welcome.
Thank you.
Sorry to hijack your session.
No, that's all right. That's all right.
I was curious.
Yeah, I'm curious too about the gear because I haven't still gone through it, but it's an exciting also thing to explore the gear design.
Okay, thank you.
Thank you.
Well, my pole number is fixed because of the magnet.
Your port number to the left, Kevin. Oh, yeah, there you go.
Yes.
Can you stand on the other side?
Sure.
Thank you, Elie. The next presentation is by Phuc. The topic of his presentation is wind turbine maximum power point tracking via integrated generator-rectifier system.
Okay, hello everyone. Thanks for being here today. I know today is a full day, but I promise this is not a lie. This is my research topic, and hopefully there's some truth in that. Yeah, so the topic I'm talking about is wind turbine maximum power point tracking the integrated generator-rectifier system. So first of all, why maximum power point tracking? Because when you put the a wind turbine out there, you want to extract the most power out of the wind, so you can sell the electricity for the largest amount of money. So that bring down, that generate you more revenue, and based on that revenue, you can feed your worker, you can do maintenance, so you keep the wind industry alive. So that is the reason why you really need to do maximum power point tracking. You don't want to waste the resources. Kevin, it doesn't move. Yes. Okay, so let me go through some background on the wind turbine, on the maximum point of a wind turbine. So imagine if you have a wind turbine and you have the wind that blowing at a certain speed, then what you have is you have an available of energy stay in that wind. However, you can, due to the mechanical constraint and due to some law of physics, you cannot get all the power out of the wind. There's only a maximum amount of power you can get out of the available amount of power in the wind. And that's so if you look at a wind turbine, there's two things you probably want to look at. The first is the two variables that is changing. The first is the air velocity. That depends on the day, the time. Like it means that how fast is the wind is blowing. And the second is the rotation speed of the wind turbine. So the air velocity, if I normalize here, will give you a 1 per unit of power. But depend on the angular speed of the wind turbine, you have a curve that tells you how much power you can extract from the wind. So the amount of power you can extract from the wind is actually a function of the tip speed ratio, but tip speed ratio is again the rotation speed of the wind turbine. So your goal here is you always want to control the wind turbine such that you stay at this maximum point. So that is what you do with. So you control the wind turbine by some way, and you ensure that the angular velocity of your wind turbine will make it operate exactly at the peak. So that is what you do to ensure maximum power point tracking. For the rest of the talk, I have the three things I will go over. So based on the background information, I will talk about some existing methods people have proposed for maximum power point tracking. And if you have been here long enough, then you all know that since last year I have been working on a thing we call the integrated generator-rectifier system, and how to use this system to perform maximum power point tracking will be the second point. And the last point is I will show some simulation and some preliminary experimental results to illustrate the concept. So how do you do, what are the methods available for maximum power point tracking? So remember, this is the curve we are having, and it depends on two things, like it depends on the maximum on the wind speed. So, and I go here, for each wind speed, you take the wind speed, multiply with the curve, and you plot one individual curve for each wind speed. What you will have is for each wind speed condition, what is the maximum power you can extract from the wind. And because this is the power, it's proportional to the cubic of wind speed, so you will see this is the power curve. So with a wind turbine design, this information is available. And what you need to control your electrical system, it needs to change. So it will measure the tip speed of the wind turbine, and depending on the tip speed of the wind turbine, it will decide how much power is it extracting. And magically, just by doing that, you will force your wind turbine to operate at a maximum power point. This is how does that happen. So look, for example, if I take a wind turbine power curve, which is the green curve, and the dash, I try to make yellow. Let's make it yellow. The dash curve is where you operate your electric power system. So say if you at a speed of 40, tip speed of 40 meters per second, and this point is where you, the electrical power you extract from the system. However, like here, at the blue curve, that is available power on the wind speed, on the wind turbine. So you have this, like the difference between the two is the excess power. How much mechanical power is higher than the electrical power. So because you have excess power, then your wind turbine will speed up, right? You have a generator, you couple to a generator, you have a wind turbine coupled to a generator, and this power is present the electrical power output, and this is mechanical power input. Then you have the difference between the two. You have some excess power, and that power will speed up your wind turbine. And if you just keep doing do the same thing, then we'll come to this point exactly at the maximum power point, where electrical power and mechanical power is exactly identical. So there's no more excess power for speeding up or slowing down. So your wind turbine will operate exactly at the maximum power point. So this is, the first method is based on power control, and then you achieve the maximum power point operation. For me, I prefer to use the notion of power, but a lot of literature you will see that is, it relies on torque control. So torque control, basically you take the same curve, you divide it by the speed, and you get to the torque. So the same, very similar, I think identical concept, it can be used for the torque control. So if I do the same thing, this is the torque versus speed capability of the wind turbine at each wind speed. And you will have the curve that represents the torque such that the power is maximum. So what you see here is the torque you want to draw will not be at the maximum torque. That is because here you divide it by V squared instead of V cubic of the V in the power case. But regardless of what you're doing, what you really need to know is the maximum torque curve, and you use that to control your wind turbine. So for example, in this case, the blue curve is for a given wind speed condition, the blue curve is a torque produced by the wind turbine. And the yellow curve is the torque you should control your generator to chase the yellow curve. And for example, at 40 meter, a tip speed for 40 meter per second, you make your generator to generate 0.9 million Newton meter of torque. And at that condition, your wind turbine will have 3.2 million Newton meters. So you have some excess torque to speed up. And if you keep doing that, you will end up at the point where the power is maximized. So is it clear to this point about the power control and the torque control? So the benefit, yes?
So this is working based upon pre-calculated reference values for the system?
Yes, so when you buy a wind turbine, people will test it already and give you this information. Okay, so the benefits of this one, okay, given you buy an expensive turbine.
Well, that's what I mean. I mean, this is like based on a table of performance values for the machine, whereas the other one is basically a direct calculation.
Excuse me?
The previous method is basically a direct calculation of power, whereas this depends upon known characteristics of the electric.
I think like both will depend on a known characteristic. One is a power and one is a torque. So if you take the curve, the power curve here, you divide by the tip speed, then you will go to exactly to this curve. Yeah, so both are the same information. It's just like which community are you talking to.
But if you're measuring one versus the other, you adjust your torque to maximize your power.
Mm-hmm.
But if you don't know, you're not maximizing torque.
No, we don't maximize.
So it's like there's one could be easily implemented feedback, the other one has a feed forward of some kind based on a pre-calculated table.
You can both do feedback. So if you do this one, your feedback signal will be the torque. And if you do this way, your feedback signal is the power. So later, if I move to the control architecture, you will see it doesn't matter which one we are using.
I agree, it doesn't matter.
Yes.
I agree with you. This makes a lot more sense, though, because you're directly...
Yeah, because we say we want to maximum power point. We want to maximum power. What is the point of controlling torque, right? Why don't you just control power?
You always look at your...
Yes, it makes more sense to me, but a lot of literature, they go to this one because conventionally the motor, when you talk about the motor control, you talk about the torque, but you talk about a generation system, then you move to the power.
So if you talk to power electronics guys, they would love to power. If you talk to machines guys, they would like to
They
power.
love torque. So we start.
But at the end of the day, you both need in both of these, those dashed lines, manufacturer data. Here you need torque, and in the previous one, the dashed line is the power. Both are manufacturing data. That is given, go back to your previous.
Yes.
This maximum power curve, the dotted line, that you need from the manufacturer of wind turbine.
It's not worth belaboring, but with this approach, if you're measuring I and V essentially, or just torque times omega, you could perform Perturb and observe and get.
I think it's going to.
Oh yeah. So let me. I have that method as well. So what is the benefits of this one? It's fast. Yeah, so under like because if you do control, the torque control is the fastest control loop you can achieve. And under like a fast varying wind speed, if you have this, you can make the wind to perform like really well, like fast tracking. Another method, easier. You don't need manufacturing data. You don't need anything. What you do is you start at a point and you perturb your speed and you observe the output power. So let's say, let's just playing a game. You have a knob to control to perturb the speed. Then you increase the speed a little, you see increase the power, then you keep increase the speed. And then if you observe that a reduction in the power, then you reduce the speed. So for example, if you do some speed step, you will eventually, given the wind condition doesn't change that fast, you will end up under to this point. So there's a lot of literature talking about like how do you deal with designing the step. But from my perspective, this is like much slower than compared to the torque control. So if I'm asked to design a control strategy, I will pick the other method because that is faster. So now that is all the background information, and here I go back to the integrated generator-rectifier system and the control architecture we are using. Okay, so the integrated generator rectifier we are proposing is based on a multi-port synchronous generator, and we have each port feed one passive. Each port will feed either passive rectifier or active rectifier, and we already showed that the configuration to give you the optimum, like the lowest voltage rating on the active rectifier, is based on one active rectifier, and then you series connecting all of them to form a DC bus. So in the context of wind turbine, that DC bus will connect it to a grid. It shouldn't be DC here. It could be either. Oh, it has to be DC grid. So the grid interface. So if you talking about like the existing wind farm, the collection system is commonly AC system. But why I put the DC here? Because although they do AC collection system, they still have used, if it were permanent magnet synchronous generator, they still have the back-to-back converter. So with the back-to-back converter, there's a DC link in between the grid side and generator side, and that form just a DC collection. So if we move into the future when people proposing the DC collection system, this block represents that DC grid. So in either case, from the generator side converter point of view, it always feed power to a DC grid. So what do we need? So now I prefer to use the power control. So if I do power control, the DC grid here has a voltage already fixed by the grid side converter. In order to control the power, what I really need to do is just control this DC bus voltage. This DC bus current. And it may not come to obvious, doesn't become obvious here. So say, if I have active rectifier, yes, you can control the current flow, but what about passive rectifier? You cannot do anything with the passive rectifier because for us, it's just diode and you don't have any control degree of freedom there. But thanks to, in the next slide, I show that thanks to this series connection architecture, you can use the active rectifier to control the DC bus current. Whatever current you put out on the active rectifier, there is just a mechanism to couple that current to the passive rectifier. So that is, I think that is the aha moment when we look into this architecture. Okay, so let's say, to be simple, let's consider an architecture with one active rectifier and one passive rectifier. So what you see here is the DC bus voltage is already fixed, and the VP here is also fixed because it is clamped directly to the back EMF from the generator, and the L and R are passive components. The value doesn't change, right? So VP is already fixed. So it means that the VA on your active rectifier is already fixed. And because that is active rectifier, so by the power balance equation, you can control the D component of the current on the AC side. VA is already fixed, so therefore you can control the DC current. And the DC current in the series architecture is the same for this loop. It means that you control the DC current going out of your active rectifier, and because of the series connection, that DC current will be the same as the current going out of the passive rectifier, and at the end of the day, you will achieve the DC bus current flowing into the DC current flowing into the DC bus. So this is the basis for the rest of the work. So we show here. So in order to achieve the current control, we use the standard DQ current controller. So one current controller for D-axis current and another current controller for the Q-axis current. Current controller is fairly simple to construct. It's just basically a PI controller with a feed-forward term. So at the end of the day, you put in the ISD star, what is the command current you want, and this controller will give out the actual ISD current that you want. And by that ISD, you can control the DC bus current. And so when you already have the current control capability, it means that you can control the power. Then you put another MPPT controller to decide what is the ISD star you need for each wind condition. So that is another like outer loop controller. And with this controller, you can do either power or torque control. So what you, at the end of the day, what you do is you take the measurement of the rotational speed of your wind turbine, and you compare it to the torque speed characteristic that I just showed before, and it will give you what is the PDC, what is the reference power you need to track. And we already showed that is this an analytical relation between the power and the D-axis current. And that is go to ECC 2019. So if you follow that publication, you will see the analytical relation. And when we solve for that, just send the ISD reference to the current control. Yes?
You're controlling machine field.
Machine field. The D-axis current. Yeah, I wasn't sure on that point. You have a comment on the machine field?
Come on. Whose work is this?
Yeah, it's my work. Yeah, but I'll.
D-axis current for him is the quadrature axis, so his axis is reversed. His D-axis is not magnetizing current. His D-axis is quadrature torque producing current. The way he set it up, is that correct?
Yeah.
Okay.
So you mean like field is the often D. Yeah, but I got it flipped here. The D is a component I use to control the torque, and by that I control the power. Yeah.
So in generator, typically you do is, so it depends on how you, no, I won't screw it up later.
Okay.
Thank you.
Yeah. So with that, so with the same architecture, we can do also the perturb and observe block diagram. So we make a perturb algorithm here, and we take the speed, we perturb the speed a little bit, and we observe what is that the power output, and then we compare with the previous step to see if it increase or decrease, and we decide the next step. So it as long as we figure out the current controller part, the rest doesn't. It just depends on what MPPT algorithm you want to use. And some simulation and preliminary experiment result. What we simulate here, I want to show the dependencies between the D-axis current and the DC bus power, because that's crucial. That is what what we rely on to do the MPPT. So on the simulation, we do that. So here is we change the D-axis reference current, and because we change the D-axis reference current, the phase A current of the amplitude of phase A current of the active rectifier will increase as well. And the bottom plot is a diode bridge phase current. You see it will follow the amplitude of the active rectifier phase current. So you increase the amplitude of phase A current of the active rectifier, then the amplitude of the diode bridge current will increase as well. It will follow. So that is why because of the series connection. Then by controlling the the current coming out of the active rectifier, then you indirectly achieve the current control on the passive rectifier as well. And so here in this simulation, I show by stepping the D-axis current, we can step the DC bus current, and by stepping up the DC bus current, we'll achieve the step in the DC bus power. So this simulation confirmed that actually when we control a D-axis current of an active rectifier, we can control the current flowing into the DC bus. And then we go and implement that on the experimental system we have in the lab. Yes?
Sorry, could you go back to
What is constant?
Like the torque on the driving machine, or the speed of the driving machine?
So here, what we keep constant is actually only what constant is the speed is constant, and the DC bus voltage is constant. So we show that the shaft speed is constant. So we show that by for a given shaft speed, we can draw various level of the power. So based on that, we can do speed up or slow down. And when we move to the next step, we can do the same thing to speed up or slow down. Yeah. And we go to our experimental setup. We have a rectifier series connection with an active series connected with the two passive, and it forms a DC bus, and it feeds to an electronic load. So this electronic load will keep the DC bus voltage to be constant. We operate in constant voltage mode. So make this one looks like a DC grid from our perspective. And we have the controller of that dyno. So at this moment, we keep the speed of that one to be constant. Keep the dyno run in the speed mode, keep the speed constant. And then what we do is we vary the D-axis current of the active rectifier. And as you see, because we vary the amplitude of the, we vary the axis current lead to the variation of the amplitude of the phase A current. And the phase current in the active rectifier will cause a change in the phase current of the diode bridge. And eventually it will lead to a change in the total DC bus current. So by this, we illustrate, in fact, experimentally, by control of the axis current of the active rectifier, we achieve the power control into the DC bus. So